Okay, so we have a 240 volt potential difference across these two parallel plates, and we have our charge here, Q, of 5 microcoulombs that is starting at the positive plate at rest. And we want to know how much time passes before this little ball with a mass of 12 grams strikes the negative plate. Obviously, this proton, or this positively charged thing, is going to want to follow these electric field lines, which are uniform, and they point from the positive plate to the negative plate. Now, the electric field in between these two plates, so what's happening is we've got, the force that's acting on this charge is QE, okay? And that's the charge Q, right, multiplied by the electric field that the charge is immersed in. So we're not using KQ over R squared here, right? Because the electric field in question is not the electric field of a point charge. Instead, we have a point charge that is moving within a uniform electric field. Now, the electric field between two plates can be found with 4 pi KQ over A, but I don't know Q and I don't know A, so I'm not going to bother with that. But it can also be found with the potential difference divided by that distance, D. So if I take 240 volts divided by 0.006 meters, I get 40,000 volts per meter for my electric field. Okay, it's uniform, it's 40,000 volts per meter. Okay, so we want to know the final velocity of this ball before it strikes the plate. So there are two ways to do it. We can start with, I guess, the sum of all forces is equal, in the y direction, is equal to ma. And, okay, the forces acting on this charge, we've got the electric force that points up, and then we've got the gravitational force that points down. Sorry. Okay, and if I make up positive, right, that's going to be my sign convention in this problem. Up is going to be positive, down is going to be negative. Then we've got plus the electric force minus gravity is equal to ma. Okay, the electric force is QE, gravitational force is mg. All right. So let's see, that's going to be 5 times 10 to the minus 6 multiplied by that electric field of 40,000. And then the mg term is 0.012 times 9.8. And that's going to equal 0.012 times the acceleration. Okay, so the electric force, if I take 5 times 10 to the minus 6 and multiply by 40,000, I get 0.20. And then for gravity, I get 0.1176. Okay, so the electric force is greater than the gravitational force, therefore it's going to move up. If the gravitational force were bigger than the electric force in this problem, then we wouldn't be able to solve it because the charge would just sit here parked on the positive plate, and the problem wouldn't make any sense. Okay, so this adds up to 0.0824, and then if I solve for the acceleration, I get 6.87 meters per second squared. Alright, so now I know the acceleration. I also know the distance that it's going to travel, delta s, is 0.006 meters, and I also know the initial velocity. Therefore, I can use that in my equations of motion. I can say that delta s is equal to v naught t plus 1/2 at squared. So 0.006 is equal to 0 plus 1/2 at squared. So t squared is 0.006. Then if I do a little calculation here, I get t squared is 0.00175, and t is 0.042 seconds. There's the time I'm looking for. Now I could also do this problem using work energy. I could say the sum of the works done by all the forces is equal to the work done by the electric force plus the work done by gravity. Those are the only significant forces in the problem. And that's equal to the change in kinetic energy. Now that initial kinetic energy, since V0 is 0, this term is 0. Now the work done by the electric force is, I guess, QE delta S. Right, we can use, okay, so to find the work, right, remember we've got three ways to find work. The work done by a force can be given as F delta S cosine theta. And this time we can use this because everything is uniform. The forces are uniform and the angle is uniform. And so here's the force, here's the distance, and then cosine theta, well, theta in this case, since the force and the distance are in the same direction, theta is equal to 0, so cosine theta is equal to 1. Now for gravity, the work done is going to be minus mg delta S. Okay, because gravitational force is mg, the displacement is delta S, but you can see up here that gravity points down, but delta S points up. And so this cosine term is cosine 180, which is negative 1. Alright, so let's see, this is 1.2 times 10 to the minus 3, and this is 0.706 times 10 to the minus 3. That's equal to 1/2 times 0.012 v squared. And then if I solve for v, I get 0.29 meters per second. Okay, well, now I know v, I know delta S is 0.006, and I know V0 is equal to 0. So again, I can use my equations of motion with constant acceleration to write delta x, or delta S, I guess in this case. Let's start over. Delta S is 1/2 v plus V0 t. So 0.006 is 1/2 times 0 plus 0.29 t, and then if I solve for t, I get 0.42 seconds. So you get the same answer either way.